Now let's do the same thing with spherical coordinates, where we'll take a couple of triple integrals already set up in spherical coordinates and figure out what the geometry is, and then go in the reverse direction. So with spherical coordinates, remember that the dv is a mess. In spherical coordinates, the dv, which is just dx, dy, dz in rectangular coordinates, and is r times dz, dr, d theta in cylindrical coordinates, blows up to rho squared sine phi, d rho, d phi, d theta in spherical coordinates. There's nothing you can do about that, so get used to it. You just have to be able to adapt. For example, down here, know that there's a rho to the fourth stacked up in the integral, and now two of those rows have to be part of dv, so this is rho squared dv. So one difference between these two integrals we notice right away is that this is integrating the function 1. Everything else in there is dv, and that means this is actually calculating a volume of some region, where this is integrating the function rho squared, where everything else is part of dv. And so we're not calculating a volume, we're just accumulating values of rho squared everywhere in whatever region is given by those boundaries. You'll notice that all of the limits here are constants, and if you're dealing with spherical coordinates, more often than not, you're going to have constant limits all around. If you don't, then maybe spherical coordinates isn't the best choice of coordinate system for the problem. So what you have to remember for spherical coordinates, I'll draw a little key up here, a little teeny tiny one, three-dimensional coordinate system. Rho is the distance from the origin in any direction. In cylindrical coordinates, the r is the same r as in polar. It's the distance from the origin down there in the xy plane. In spherical coordinates, rho is just the distance from the origin no matter which direction you're going in. Theta is the same theta as in polar coordinates. It's the counterclockwise angle around in the xy plane that you need to sweep out your region. And then phi is the weird one. That's the angle coming down from overhead. So for example, you would never expect a value of phi bigger than pi, because that would take you from 0 to pi over 2 all the way down here to pi. And if you had a value beyond pi, you'd be swinging back up the other side, but the better way to get there would just be to turn yourself around with a different theta and then come down from overhead with a smaller phi. Okay, so what's going on with these things? Well, this, if we match this up, theta is on the outside, theta is going from 0 to pi over 2. That means we're only using the first fourth of the xy plane. Phi is going from 0 to pi over 2. And that means, again, remember, phi is 0 is overhead. And then we come down, maybe here's pi over 4 halfway down. We're landing at phi equals pi over 2. And that's brought us all the way down to the xy plane, but no farther. And then rho is going from 0 to 1, which means no matter which direction we go in, rho is going to be lowest at 0, highest at 1. So we're going 1 unit from the origin, no matter which direction we look. So what that means is that we've taken what would have been a full sphere, and we've carved out the portion of the sphere that's only here in the first quadrant, and maybe with a different color. Can I do this? So, like this. Does that work? So the whole sphere would keep going around, on both sides, but we don't want that. We just want the portion of the sphere that's a quarter of the way around in the theta direction, half the way down from the vertical, and then going from 0 to 1 in the radial direction. So this integral would be calculating the volume of that region, right? Now, I can actually tell you what that answer is without calculating. The volume of this whole sphere would be 4/3 pi times the radius cubed, right? And that's the volume of the total sphere. We are carving out, how much is it? Let's see, just around the top half, that's 1/4 of the top half, and we're using none of the bottom half. That's 1/8 of the total sphere. And so the value of that big nasty integral would have to be 4/3 pi over 8, because that would be the volume of the unit sphere cut down to 1/8. All right, what's going on down here? Not a whole lot's changed. Theta is going from 0 to pi over 4. That's weird. Okay, well that means that down here in the xy plane, we are only carving out to the first diagonal, right? Here's the x-axis, here's the y-axis. Theta is only going 1/4 of the way around. Phi is going from 0 to pi over 2, so again from the top we're coming down all the way to the plane. And rho is going from 0 to 3 square root of 2. So wherever that is, let's say it's right here, that distance is the same in that direction, and in that direction, and in that direction. So this is, again, thinking about an entire sphere. I know I'm disappearing off the bottom of the screen with my hand there, but we actually don't need the missing parts. All right, think about an entire sphere whose radius is 3 square root of 2. There we go. And we've sliced out of that sphere a chunk which swings around from 0 to pi over 4 in the xy plane. So it's a really thin slice of that sphere. This is not calculating the volume of that slice because we're integrating rho squared instead of 1. Let me see if I can draw. I'll try to draw. So something that looks like that, maybe, where this is 0 for theta, this is theta is pi over 4. So it's just a tiny little wedge, 1/8 of the way around in the xy plane. All right, now let's go the other direction with spherical coordinates and take a description of a region and turn that into the limits that we would need to use on the integral. Three-dimensional coordinate system. Template for the triple integral, which in spherical coordinates, remember, dv is rho squared sine phi, d rho, d phi, d theta. And then we're integrating, we would be integrating whatever. If we were finding a volume, this would be 1. If we were integrating a function, this would be the spherical version of whatever that function is. What does this region look like? Well, it's a sphere of radius 4 to start with. So let's see if I can do that. Okay, apart from that miss over there on the right, that's still pretty horrible, but we'll work with it. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so there's 4 units in every direction. But we only want this sphere cut out. We only want this sphere for points that have a positive y coordinate. So I suppose I should be labeling things, right? X, Y, and Z. And so that means we only want the parts of this sphere that are looking forwards into the positive y-axis, or in other words, if we look down from overhead to the xy plane, we would only be looking at these points. So in other words, we had this big sphere to start with, and then here comes a giant slicer that just cuts right down through the paper, takes away the half of the sphere, goodbye, which has negative y coordinates, and leaves the forward half of the sphere with positive y coordinates. Now we're still keeping top and bottom, right? We're still keeping points in the sphere that have positive y coordinates for negative z and for positive z. The y coordinate is the only restriction that we have. So what does that do for our limits? Well, If we're doing dv is d rho, d phi, d theta, then here's our rho integral, here's our phi integral, here's our theta integral. Theta is the radial theta, famous from polar coordinates. We can see that from this diagram is going to go from 0 to pi. Pi over 2 would be a quarter, 2 pi would be all the way around. We want theta to go from 0 to 2 pi. From the fact we are taking this whole sphere, we still are going to go from the top to the bottom all the way down as long as we're going in the positive y direction. That means that phi is going to go from 0 to pi. Right? Here's phi equals 0, phi equals pi over 2, phi equals pi. And then rho is going to go from 0 to 4. Because we're looking at a sphere of radius 4, so in any direction that we're looking, our radial distance starts at 0 and then goes out to 4. And there we go. 6 constant limits for spherical coordinates. Adjust these for different configurations, like say this said set up limits for a triple integral that uses a sphere of radius 4 for y greater than or equals 0 and above the xy plane. Then that would mean we're going to throw away the bottom half of the sphere, which means that phi would go from 0 to pi over 2. 0 to pi over 2. So you can make all sorts of adjustments depending on which part of the sphere you're keeping or throwing away.